The universe is larger than we can fully imagine. There are hundreds of billions of galaxies. Each galaxy holds hundreds of billions of stars. Around many of those stars, planets orbit. We now know that planets are common. Some sit at just the right distance from their stars for liquid water to exist. On Earth, once the planet cooled and oceans formed, life appeared relatively quickly. It did not begin with intelligence or complexity. It began with chemistry that could copy itself and draw energy from its surroundings. That chemistry proved resilient. Life on Earth survives in boiling vents, frozen deserts, crushing pressure, and intense radiation. It adapts to conditions that once seemed impossible. If the ingredients are common and the universe is vast, then the question becomes difficult to ignore. Where is everyone? Mars once held rivers and lakes. Robotic explorers search its rocks for signs of ancient microbes, not living creatures, but traces of what may have existed long ago. Beyond our solar system, telescopes detect planets in increasing detail. Atmospheres are measured, signals are filtered, data improves, so the mystery remains. Is life rare, and are we early, alone, or simply misunderstanding life itself? Tonight, we will follow only what science can measure, test, and verify, not speculation, not stories of visitors, only evidence, limits, and the unanswered questions that remain. If you're already enjoying this peaceful moment of wonder, it would mean so much if you gave this video a like, or subscribed if you'd like more sleepy science stories like this. And if you don't mind, tell me in the comments where in the world are you watching from tonight, and what time is it there. I love watching our bedtime map grow, one curious dreamer at a time. So now take a deep breath, let your shoulders relax, and let's begin. In laboratories lit long after midnight, and in quiet rooms where data flickers across silent screens, the word life is handled with unusual care. It is smaller than forests and quieter than animals. It does not require thought, motion, or even visible form. Intelligence is an ornament that arrived late, movement a strategy rather than a requirement. When scientists speak of life, they are tracing something more fundamental, something that begins long before eyes or wings or language. At its core, life is recognized not by appearance but by process. It must sustain itself through chemistry, maintaining an internal order against the constant pull of entropy. Within a living cell, molecules are not scattered randomly. They are arranged, repaired, and replaced through networks of reactions that draw energy from the surrounding environment. This energy can come from sunlight, from chemical gradients, or from compounds that would seem hostile to most familiar organisms. What matters is not the source, but the steady flow, the ability to harness it to build structure and maintain balance. Growth follows naturally from this chemistry. A living system takes in raw materials and incorporates them into itself, extending its complexity without surrendering cohesion. Reproduction extends that pattern further still, copying information into a new structure capable of repeating the cycle. Information is central here, usually stored in DNA or RNA on Earth, guiding the assembly of proteins that carry out the work of metabolism. The specific molecules may vary in theory, but the pattern of encoded instructions and self-directed construction remains essential. Other phenomena mimic pieces of this behavior without fulfilling the whole. Fire spreads, consumes fuel, and releases energy, yet it does not enclose information or regulate its reactions from within. Crystals grow into elegant shapes, organizing atoms into repeating lattices, yet they do so passively, guided by external conditions rather than internal instructions. Machines process energy and perform tasks, but they lack autonomous chemistry and do not reproduce themselves through encoded biological information. Each resembles life in fragments, but none achieves the full integration of metabolism, growth, and heredity. Viruses hover at the boundary and unsettle this framework. They carry genetic material and evolve over time, yet they cannot replicate without hijacking the machinery of a host cell. Outside that borrowed environment, they are inert particles suspended between chemistry and biology. Their ambiguity reminds researchers that any definition must remain flexible enough to accommodate complexity without dissolving into vagueness. This careful framing shapes every instrument sent into space and every spectrum analyzed from distant atmospheres. Scientists search not for cities or signals, but for signs of persistent chemistry, out of equilibrium, gases replenished against expectation, molecular patterns that hint at organized replication. The definition acts as both guide and filter, narrowing the search to processes that can be measured. Yet there remains an awareness that unfamiliar forms may operate beyond current categories, and that caution must balance precision so that genuine biology, if it differs from Earth's example, is not overlooked in the vast quiet beyond our world. There was a time when biology seemed neatly bounded by comfort, as if life preferred the same narrow conditions that human bodies do: warmth within reason, light from above, air that could be breathed without harm. The edges of those assumptions felt firm and reassuring. Then the edges dissolved. In the late 20th century, submersibles descended into the crushing dark along mid ocean ridges and revealed towers of black smoke rising from the seafloor. Hydrothermal vents poured mineral rich water, heated beyond boiling at the surface, dense with dissolved metals and sulfur compounds. Around those vents, in pressure that would collapse most familiar forms, entire ecosystems thrived. Tube worms taller than a person anchored themselves near the scalding plumes, sustained not by sunlight, but by bacteria living within their tissues. These microbes performed chemosynthesis, extracting energy from chemical reactions between hydrogen sulfide and seawater, building organic molecules in total darkness. The discovery reshaped marine biology in a single sweep. Elsewhere, in pools heated by volcanic springs, microorganisms multiplied in water that would blister skin within seconds. Thermophiles stabilized their proteins and membranes with molecular adaptations that prevented heat from unraveling the delicate bonds of life. In polar ice sheets, microbes endured temperatures far below freezing, their metabolic rates slowed to a near whisper, yet never fully silent. In the pores of Antarctic rocks and within briny veins trapped in ancient glaciers, cells persisted in conditions once assumed sterile. Deep beneath continents, kilometers underground, life was found embedded within rock fractures and aquifers cut off from the surface for millions of years. These organisms derived energy from the slow decay of radioactive elements or from reactions between water and basalt, processes that required no daylight and no seasonal rhythm. Entire microbial communities existed without any connection to the photosynthetic world above, sustained instead by geology itself. Radiation, acidity, pressure, and salinity lost their status as absolute barriers. Organisms were discovered that could survive doses of ionizing radiation capable of shattering DNA into fragments, repairing their genomes with precise enzymatic choreography. Others flourished in acidic lakes with pH values rivaling battery fluid, or in hypersaline basins where salt crystals formed crusts across the shoreline. Sunlight, once considered the primary engine of life, was revealed as only one of several viable energy sources. The essential requirement was not illumination, but a gradient, some chemical or physical imbalance that could be tapped and transformed. With that realization, habitable territory expanded far beyond temperate surfaces. Oceans locked beneath ice, planets without bright stars. Even the interiors of rocky worlds gained new relevance. The map of possibility stretched outward almost overnight, not through speculation, but through observation. If life on Earth could occupy boiling vents, frozen deserts, buried stone, and endless night, then the boundary between living and unlivable was thinner than previously believed. Biology proved less fragile and more inventive than the narrow corridor once imagined, and the search for life beyond Earth quietly widened to include environments that had once seemed utterly barren, far from forests and coastlines. In places rarely imagined as lively, Earth carries forms of biology that seem to belong to another planet. Beneath mineral crusts, within acidic pools tinted by dissolved metals, and inside stones that appear inert, microorganisms persist in quiet abundance. They do not depend on leaves or light. Their existence unfolds at scales too small for the eye, yet their chemistry reshapes entire landscapes. Some of these organisms draw energy directly from inorganic compounds, weaving metabolism from reactions that most complex life would find toxic. Sulfur oxidizing bacteria flourish where volcanic gases seep through rock, converting hydrogen sulfide into usable energy while leaving behind deposits that stain the ground in pale yellows and whites. Iron metabolizing microbes extract electrons from ferrous minerals, transforming the chemistry of groundwater and carving rust colored patterns along subterranean channels. Others consume methane rising from buried organic matter, linking deep carbon reservoirs to the atmosphere through invisible biochemical pathways. In each case, life anchors itself not to sunlight, but to chemical disequilibrium, turning gradients into sustenance. There are organisms known as radiotolerant bacteria that endure levels of ionizing radiation capable of fragmenting genetic material beyond recognition. Within their cells, enzymes tirelessly reassemble broken strands of DNA, restoring continuity through mechanisms that remain subjects of detailed study. These adaptations reveal a resilience rooted not in avoidance but in repair, an internal choreography that counters molecular damage with precision. In arid deserts exposed to intense ultraviolet light, similar strategies shield cellular components, using pigments and protein structures to absorb or dissipate energy that would otherwise prove lethal. Earth's deep subsurface biosphere stretches kilometers below ground, where pressure mounts and nutrients are scarce. Microbial communities, embedded within crystalline bedrock, metabolize at astonishingly slow rates, dividing perhaps once in centuries. Their environment resembles no familiar ecosystem, yet it remains chemically active, shaped by interactions between water and rock. In hypersaline lakes, salt concentrations approach saturation, forcing cells to balance osmotic pressure with specialized proteins and compatible solutes. Even in these concentrated brines, life constructs membranes, synthesizes enzymes, and reproduces with measured persistence. Such environments mirror conditions once considered exclusive to distant moons or ancient planetary surfaces. Acidic rivers recall the chemistry expected near volcanic exoplanets. Methane-rich sediments resemble atmospheres observed around outer solar system bodies. The realization that Earth hosts analogs of these settings compresses the perceived distance between home and cosmos. Habitability, once imagined as a narrow band defined by temperate climates and breathable air, expands into a spectrum of chemical possibilities. The lesson carried by these organisms is subtle yet profound. Life does not demand comfort, it requires opportunity, a source of energy, and the capacity to organize matter against entropy. By studying these alien seeming inhabitants of our own planet, scientists refine the criteria used to evaluate distant worlds. Habitable becomes less a description of familiar landscapes and more a recognition of dynamic chemistry capable of sustaining self-directed complexity. Earth, in holding such extremes, serves as both laboratory and reminder that biology may flourish in forms far stranger than surface impressions suggest. Long before its surface settled into the cold stillness seen today, Mars carried the markings of flowing water. From orbit, dry channels branch across its deserts in patterns that resemble terrestrial river valleys, converging toward basins that once held standing lakes. Sedimentary layers rise along crater walls, stacked and curved in ways that suggest slow deposition in ancient shorelines. Mineral veins trace through fractured rock, left behind by groundwater that once moved beneath a heavier sky. These features remain etched into the terrain, quiet records of a wetter chapter. Billions of years ago, evidence indicates that Mars possessed a thicker atmosphere composed largely of carbon dioxide, capable of trapping heat through a greenhouse effect. Temperatures may have allowed liquid water to persist across broad regions, pooling in impact craters and carving pathways through volcanic plains. Clay minerals detected by orbiting spectrometers form only in the presence of sustained water, preserving chemical signatures of a time when interaction between rock and liquid was prolonged and stable. Delta formations at the edges of certain basins reveal where rivers once delivered sediments into larger bodies, building fan-shaped deposits grain by grain. Yet Mars is smaller than Earth, and its interior cooled more rapidly. As its molten core solidified, the global magnetic field weakened and eventually disappeared. Without that magnetic shield, the atmosphere became exposed to the steady pressure of solar wind, a stream of charged particles flowing outward from the sun. Over immense spans of time, those particles stripped lighter molecules into space. The thinning air reduced surface pressure, allowing water to evaporate or freeze, its remaining traces retreating into polar caps and subsurface ice. The loss of atmospheric density altered temperature regulation, leading to greater extremes between day and night. Ultraviolet radiation reached the ground with little obstruction, breaking down organic compounds that might otherwise have accumulated. Chemical weathering slowed as liquid water became rare. The transformation did not occur in a single moment, but through gradual erosion of conditions once favorable to life's chemistry. Today, robotic explorers traverse this altered world with deliberate patience. Rovers analyze sedimentary rocks in dried lake beds, drilling into fine-grained mudstones that could preserve microscopic textures formed in calm water. Instruments measure the isotopic composition of gases, study mineralogy at microscopic scales, and search for organic molecules embedded within ancient deposits. The focus is not on detecting active organisms, but on identifying biosignatures, patterns, or chemical imbalances that could indicate past biological activity. If life ever emerged on early Mars, current conditions make survival at the surface unlikely. However, protected niches beneath the ground, shielded from radiation and temperature swings, remain subjects of careful investigation. Even so, the prevailing expectation centers on fossils rather than living cells, subtle traces locked within rock layers that formed when water still flowed freely. Mars stands as a testament to planetary fragility, a reminder that habitability can fade, leaving only geological memory to suggest what might once have begun there. Beneath a surface of fractured ice, far from the warmth that shapes familiar climates, a different kind of ocean moves in darkness. Europa, one of Jupiter's largest moons, presents itself as a sphere of pale bands and jagged lines, its crust etched by stress patterns that hint at motion below. Those markings are not random. They suggest an outer shell floating atop liquid water, a hidden ocean kept from freezing solid by forces that operate without sunlight. Measurements of Europa's gravity field and magnetic interactions with Jupiter indicate a vast reservoir beneath the ice, likely a global ocean that may exceed the combined volume of Earth's seas. Instead of waves breaking against open air, this water is sealed beneath kilometers of frozen crust, insulated from space by a rigid barrier that both protects and conceals it. The presence of such an ocean at this distance from the Sun once seemed improbable, yet the mechanism sustaining it lies in tidal heating. As Europa orbits Jupiter, gravitational forces flex its interior, generating frictional warmth deep within. That steady kneading converts orbital energy into heat, preventing complete solidification. Within this subsurface ocean, conditions may resemble environments already known in quieter corners of Earth. If Europa's seafloor interacts with a rocky mantle, chemical exchanges between water and mineral surfaces could release compounds such as hydrogen and other reduced molecules. These substances form chemical gradients, the kind that on Earth support ecosystems independent of photosynthesis. The potential presence of salts detected in surface fractures strengthens the case for a chemically active ocean beneath, one where dissolved minerals circulate and possibly sustain ongoing reactions. Unlike distant exoplanets inferred only through light curves and spectral signatures, Europa offers the possibility of direct exploration. Plumes of water vapor have been tentatively observed rising above its surface, suggesting that material from the ocean might reach space through cracks in the ice. Such features provide a rare opportunity to sample interior contents without drilling through the entire crust. Even without confirmed plumes, the very existence of a stable, long-lived ocean expands the concept of where liquid water can persist. The absence of sunlight does not equate to the absence of energy. On Europa, warmth arises from gravitational interplay, and chemistry may be fueled by interactions at the ocean floor. Habitability becomes less about proximity to a star and more about sustained internal dynamics. This realization has elevated Europa to the forefront of astrobiological interest. It embodies a category of worlds where water is abundant, energy is plausible, and isolation from harsh surface radiation might allow complex chemistry to endure over immense spans of time. In the growing catalog of potential habitats beyond Earth, Europa stands quietly but insistently near the top. Its concealed ocean, larger than any on our planet, represents not speculation but measurable physics and observable data, a reminder that life's essential ingredients may gather in places once dismissed as too distant and too cold to matter. Sometimes, discovery does not come from digging downward, but from watching what rises. Enceladus, a small moon of Saturn, revealed itself not through subtle gravitational signatures or distant spectral hints, but through motion visible against the blackness of space. From its south polar region, vast plumes of water vapor and ice particles stream outward in luminous arcs, escaping through fractures in the frozen crust. These geysers extend hundreds of kilometers above the surface before dispersing into Saturn's E ring, transforming a quiet moon into an active participant in its planetary system. Data gathered during close flybys showed that these jets are not composed of simple water alone. Instruments detected organic molecules, salts, and molecular hydrogen within the escaping material. The presence of such compounds indicates that the source reservoir beneath the ice is not inert. Salinity suggests prolonged contact between liquid water and rocky material, while molecular hydrogen points toward ongoing chemical reactions at elevated temperatures. In particular, the interaction between water and certain minerals can produce hydrogen through a process known as serpentinization, a reaction that, on Earth, occurs in hydrothermal environments along oceanic crust. Evidence now supports the existence of a subsurface ocean beneath Enceladus's icy exterior, maintained in liquid form by tidal forces exerted by Saturn and neighboring moons. As Enceladus follows its slightly elliptical orbit, gravitational stress flexes its interior, generating frictional heat. This internal warmth prevents the ocean from freezing entirely and may power hydrothermal vents at the seafloor. Such vents, if present, would create chemical gradients capable of sustaining metabolism in the absence of sunlight. The parallels to Earth's own deep marine ecosystems are compelling, yet here the sampling occurs not beneath kilometers of ocean, but in the vacuum of space. The fractures near the South Pole, sometimes called tiger stripes, act as conduits between the concealed ocean and the exterior. Material from below ascends through these openings and is expelled into orbit. This process offers an extraordinary advantage for exploration. Spacecraft do not need to drill through thick ice to access potential biomarkers. By flying through the plumes, instruments can directly analyze ocean-derived particles and vapor. During the Cassini mission, mass spectrometers measured complex organics within these jets, confirming that fundamental ingredients associated with life exist within the moon's interior. Enceladus altered the hierarchy of astrobiological targets not through size or proximity to the Sun, but through accessibility. It demonstrated that small worlds can harbor dynamic oceans and that geological activity can persist far from stellar warmth. The fact that samples reach space naturally reduces the technical barriers to investigation and refines mission design priorities. Instead of imagining distant possibilities abstractly, scientists now consider trajectories that intersect with active plumes, turning a moon once overlooked into one of the most compelling locations for studying extraterrestrial habitability. Saturn's largest moon turns slowly beneath a veil the color of faded amber, its surface hidden behind an atmosphere dense enough to rival that of early Earth. Titan is wrapped in nitrogen and laced with methane, forming a thick haze where sunlight filters down as a dim orange glow. High above the ground, ultraviolet radiation from the distant sun fractures methane molecules, triggering reactions that assemble increasingly complex hydrocarbons. These compounds drift downward like a steady chemical snowfall, settling across plains and into shallow basins. Radar images have revealed lakes and seas pooled near the poles, yet these are not composed of water. They are filled with liquid methane and ethane, stable in Titan's extreme cold. Shorelines curve around dark expanses, and channels etched into the terrain appear to carry hydrocarbon rain toward lower ground. A cycle unfolds here that echoes familiar patterns: clouds forming, precipitation falling, liquids collecting and evaporating, all conducted with substances that, on Earth, would exist only as gas. The landscape carries the outline of habitability, but its chemistry runs on different rules. Within this environment, organic molecules grow steadily more intricate. Laboratory simulations suggest that Titan's atmosphere can produce amino acid precursors and other complex structures under the influence of radiation. Particles known as tholins accumulate on the surface, contributing to the moon's muted coloration. These materials demonstrate that prebiotic chemistry, the type thought to precede living systems, can flourish in the absence of liquid water. Carbon bonds assemble into networks of impressive diversity, and yet no evidence indicates that these networks organize into self-sustaining metabolism. Temperature shapes this divergence. At nearly minus 179 degrees Celsius, molecular motion slows dramatically. Chemical reactions proceed at a reduced pace, and liquid methane lacks the polarity and solvent properties that make water so effective at facilitating biological complexity. While theoretical studies explore the possibility of alternative membranes and metabolic pathways suited to hydrocarbons, direct observations have not revealed structures that clearly resemble living systems. The chemistry advances, but it does not appear to cross the threshold into replication and inheritance. Titan thus represents an invaluable counterpoint to worlds with subsurface oceans or ancient riverbeds. Here, the raw ingredients of life are abundant, and atmospheric reactions create a laboratory of organic synthesis on planetary scale. Yet complexity alone does not guarantee biology. By examining a world where chemistry thrives but life has not been detected, researchers refine their understanding of the boundaries between prebiotic processes and true organisms. In this sense, Titan contributes quietly, yet decisively, to astrobiology. It suggests that habitability depends not only on carbon and energy, but on a delicate interplay of temperature, solvent properties, and dynamic cycling capable of sustaining evolving systems. The absence of confirmed life here does not diminish its importance. Instead, it sharpens the criteria used elsewhere, reminding scientists that success and failure are both instructive when tracing the subtle conditions under which living chemistry may or may not emerge. Three neighboring worlds circle the same star, formed from similar materials, shaped in the same early turbulence, yet their surfaces tell profoundly different stories. Earth carries oceans that remain liquid across eons. Venus turns beneath a sky of crushing carbon dioxide and clouds of sulfuric acid. Mars rests cold and thin-aired, its water locked in ice or lost to space. Their shared origin highlights a quiet truth that water alone does not secure life. In their youth, all three planets likely possessed substantial atmospheres and reservoirs of liquid water. Geological evidence suggests early Mars sustained rivers and lakes, while models of early Venus indicate the possibility of shallow seas before extreme warming took hold. The divergence arose through feedbacks that magnified small initial differences. On Venus, increasing solar input, combined with volcanic outgassing, intensified the greenhouse effect. As surface temperatures climbed, more water evaporated, adding water vapor to the atmosphere. Water vapor itself is a potent greenhouse gas, trapping additional heat. This positive feedback loop accelerated until oceans boiled away, leaving behind a dense envelope of carbon dioxide and surface conditions hot enough to melt lead. Mars followed a different path. Its smaller mass resulted in weaker gravity and a core that cooled relatively quickly. As internal heat declined, the magnetic field diminished, exposing the atmosphere to erosion by solar wind. Gradually, lighter molecules escaped into space. With decreasing atmospheric pressure, liquid water became unstable at the surface, either freezing or sublimating. The greenhouse effect weakened, temperatures fell, and the hydrological cycle slowed to near stillness. Small shifts in planetary properties amplified over time, steering Mars toward aridity and cold. Earth's relative stability arises from an interplay of factors. Its mass supports long-term retention of an atmosphere, while plate tectonics recycle carbon between surface and interior, moderating greenhouse gases through the carbon-silicate cycle. The presence of a magnetic field shields atmospheric particles, reducing direct stripping by solar wind. Even so, this balance remains dynamic rather than permanent. Periods of intense volcanism or asteroid impact have altered climate dramatically in the past. Ice ages and warm intervals alternate, demonstrating that equilibrium is delicate. Liquid water is often treated as the primary requirement for life because it acts as an effective solvent, facilitating complex chemistry. Yet the mere existence of water does not guarantee stable conditions for billions of years. Temperature must remain within a range that preserves molecular structures. Atmospheric composition must allow pressure sufficient for liquid phases. Energy input must avoid triggering runaway feedbacks that push the planet beyond recovery. Habitability emerges not from a single ingredient, but from sustained balance among many variables. Earth, Venus, and Mars illustrate how neighboring worlds can diverge sharply when those variables shift, even slightly. The window during which a planet supports liquid water at its surface may open and close across geological time. In that sense, habitability is not a fixed property, but a transient state, maintained through complex interactions that can unravel as readily as they coalesce. Astronomers often draw a narrow ring around a star and shade it in soft color, marking a region where liquid water could exist on a planet's surface. This band has come to be known as the habitable zone, sometimes called the Goldilocks zone, implying a distance not too hot and not too cold. It is a useful first approximation, a way of narrowing attention within the vast architecture of planetary systems. Yet the simplicity of that ring conceals a far more intricate reality. The habitable zone is calculated primarily from stellar luminosity and orbital distance. If a planet orbits within that range, incoming radiation might allow surface temperatures compatible with liquid water, assuming a suitable atmosphere. That final assumption carries enormous weight. Atmospheric composition determines how heat is absorbed, reflected, or trapped. A thin atmosphere may fail to prevent water from freezing, while an overly dense one can trigger intense greenhouse warming. Two planets at identical distances from their star can diverge dramatically depending on the gases they retain. Pressure plays an equally decisive role. Water remains liquid only within certain pressure and temperature combinations. Even if a world resides in the nominal habitable zone, insufficient atmospheric pressure can cause liquid water to evaporate or sublimate. Conversely, extreme pressure might maintain liquid phases under conditions that otherwise appear too cold. These subtleties are not visible in orbital diagrams, yet they shape planetary outcomes. Geological activity further complicates the picture. Plate tectonics, volcanic outgassing, and long-term carbon cycling influence atmospheric stability over millions of years. On Earth, the exchange of carbon dioxide between mantle and crust helps regulate climate, preventing sustained runaway extremes. A planet lacking such processes may drift toward climatic instability despite residing within the correct orbital band. Internal heat, driven by radioactive decay and residual formation energy, affects whether a planet maintains magnetic shielding, which in turn influences atmospheric retention. Observations of exoplanets have revealed that many worlds located squarely within their stars' habitable zones appear inhospitable. Some are gas giants with no solid surface. Others are rocky but possess densities and compositions suggesting crushing atmospheres or desiccated conditions. Detection of high stellar activity around certain stars indicates intense flaring that could strip atmospheres or irradiate surfaces, undermining potential habitability even at favorable distances. Distance from a star defines only one variable in a complex equation. Habitability arises from the interplay of mass, atmospheric chemistry, magnetic fields, geological processes, and stellar behavior over time. The ring drawn around a star offers guidance, yet it cannot predict whether a planet sustains oceans, loses its air, or oscillates between extremes. As planetary science deepens, the habitable zone becomes less a guarantee and more a starting point. It frames where liquid water might persist, but it does not capture the fragile balances required for living chemistry to endure. Beyond simple orbital placement lies a network of factors that determine whether a world remains dynamic and potentially life supporting, or settles into sterile equilibrium despite residing in the right place. For most of human history, the planets known to science were only those that circled our own sun, a small and orderly family set against a background of distant stars. The assumption lingered quietly that other stars might host similar companions, yet there was no direct evidence. That changed in 1995 when astronomers confirmed the first exoplanet orbiting a sun like star, 51 Pegasi b, detected through subtle wobbles in its parent star's motion. The discovery did not merely add a new world to a catalog, it opened an entirely new field. In the decades that followed, detection methods became more refined. The transit technique measured minute dips in starlight as planets crossed in front of their stars, while radial velocity instruments tracked stellar motions with increasing precision. Space telescopes such as Kepler revealed that planets are not rare anomalies but common features of stellar systems. Thousands have now been confirmed, and statistical analyses suggest that most stars in the Milky Way likely host at least one planet. What emerged from this growing census was not a repetition of our solar system's architecture, but a startling variety. Massive gas giants were found orbiting extremely close to their stars, completing a full year in only days. Rocky planets larger than Earth but smaller than Neptune, known as super-Earths and mini-Neptunes, appeared with surprising frequency. Some systems displayed tightly packed chains of worlds, while others contained planets on highly eccentric orbits, tracing elongated paths that would destabilize familiar climates. The prevalence of super-Earths and mini-Neptunes stands out in particular. These categories do not exist in our own solar system, where terrestrial planets remain relatively small and gas giants dominate the outer regions. Many of these newly discovered worlds possess thick gaseous envelopes over rocky cores, creating environments unlike anything close to home. Their densities and radii indicate compositions that blur traditional classifications, challenging assumptions formed from a single planetary example. Statistical modeling now suggests that Earth sized planets in temperate orbits may be common in absolute numbers, yet their specific conditions vary widely. Stellar type influences, radiation levels, and activity cycles. Planetary mass affects atmospheric retention and geological dynamics. Orbital resonance within a system can stabilize or destabilize climate over long timescales. Amid this diversity, Earth appears neither uniquely improbable nor entirely typical. The expansion of known planetary systems has transformed the search for life into a statistical endeavor grounded in observation rather than speculation. Each confirmed exoplanet adds data points that refine occurrence rates and constrain models of formation. The realization that planets form readily around stars shifts the question away from their existence and toward their characteristics. Our solar system, once the only template, is now one arrangement among many. Its familiar structure, situated within a vast spectrum of possibilities revealed by light curves and spectral shifts measured across the galaxy. A distant star dims by a fraction so slight that only sensitive instruments can perceive it, and in that brief fading lies a subtle archive of information. When a planet crosses in front of its star from our vantage point, a small portion of starlight filters through the thin shell of gas surrounding that world before continuing toward Earth. Within that filtered glow, atoms and molecules leave delicate imprints, absorbing specific wavelengths and allowing others to pass. The spectrum that arrives is no longer pristine starlight, but a coded message shaped by atmospheric chemistry. Each chemical compound interacts with light in a characteristic way. Water vapor absorbs in distinct infrared bands. Methane imprints its own pattern, and carbon dioxide leaves recognizable gaps in the spectrum. By spreading the incoming light into its component colors and measuring the depth of these absorption features, scientists infer which gases are present. The process resembles reading the outline of a hidden object by the shadow it casts, subtle variations revealing composition without direct contact. Space telescopes, equipped with spectrographs, extend this technique beyond our solar system, analyzing atmospheres of planets orbiting other stars. In some cases, water vapor signatures have been detected around hot gas giants, while hints of methane and carbon dioxide appear in others. The presence of these molecules does not confirm life, but it refines understanding of planetary conditions. Temperature, atmospheric pressure, and cloud cover influence how spectral lines appear, demanding careful modeling to separate signal from noise. Transmission spectroscopy during planetary transits is only one method. When a planet passes behind its star, the combined light of star and planet decreases slightly, allowing researchers to isolate the planet's own thermal emission. Direct imaging of certain large exoplanets permits measurement of reflected starlight, providing another avenue for atmospheric characterization. Each approach carries uncertainties, shaped by instrumental limits and the immense distances involved. The faintness of these signals imposes caution. Stellar activity can mimic or obscure absorption features, and instrumental systematics may introduce artifacts that resemble genuine atmospheric lines. Clouds or hazes can flatten spectral signatures, masking underlying gases. Statistical analysis and repeated observations are required to build confidence. Even then, interpretation rests on models that assume particular temperature profiles and chemical interactions, introducing degrees of ambiguity. Water vapor, oxygen, ozone, methane, and other gases are often discussed as potential biosignatures, yet each can arise through non biological processes under certain conditions. The challenge lies not only in detection but in context. A molecule's significance depends on planetary environment, stellar radiation, and chemical equilibrium. Without understanding those factors, apparent signals risk overstatement. Light traveling across light years carries fragile evidence, reshaped by every layer of gas it encounters. Decoding that evidence demands restraint as much as ambition. Spectra provide glimpses into alien skies, revealing temperature, composition, and dynamic processes. They do not deliver certainty outright, but offer probabilities that sharpen gradually as instruments improve and observations accumulate, drawing atmospheric portraits from the faintest shifts in starlight. A single molecule drifting in a distant atmosphere can seem to carry enormous significance. Oxygen, for example, dominates discussions of biological activity because on Earth it is continually replenished by photosynthesis. Without life, free oxygen would react with surface materials and disappear over geological time. Yet planetary chemistry does not always follow familiar patterns, and oxygen can accumulate through processes unrelated to organisms. Ultraviolet radiation from a star can split water vapor high in an atmosphere, freeing hydrogen to escape into space while leaving oxygen behind. On a planet that loses large amounts of water this way, oxygen may build up to substantial levels without any biological contribution. Similarly, carbon dioxide exposed to intense radiation can produce oxygen through photodissociation under specific conditions. In isolation, an oxygen signal might appear compelling, but without context, it may reflect atmospheric evolution rather than living metabolism. Methane presents another example. On Earth, a significant fraction of methane originates from microbial activity, especially in wetlands and sediments. Its presence, alongside oxygen, suggests chemical disequilibrium, a state that life can maintain through continuous production. However, methane can also arise from geological processes. Reactions between water and certain rocks can release hydrogen, which then combines with carbon compounds to form methane in the absence of biology. Volcanic activity and thermal alteration of organic matter within a planet's crust can contribute additional sources. Observed alone, methane does not confirm a biosphere. These ambiguous signals are known as false positives, atmospheric features that resemble biosignatures but emerge from abiotic pathways. Distinguishing between biological and non biological origins requires understanding planetary context in detail. Stellar type influences ultraviolet flux and photochemistry. Planetary mass and temperature affect atmospheric escape and chemical stability. Surface composition determines which reactions are favored over time. Without integrating these variables, interpretation remains uncertain. Because of this complexity, researchers seek multiple lines of evidence before drawing conclusions. Combinations of gases that are difficult to sustain simultaneously without continuous input may provide stronger cases. For instance, the coexistence of oxygen and methane in substantial quantities over extended periods could indicate active replenishment beyond geological expectations. Detection of additional compounds, seasonal variations, or surface reflectance features might further strengthen interpretations. Each new datum reduces ambiguity incrementally. This cautious approach slows announcements and tempers excitement. Data must be re examined, models refined, alternative explanations tested. Instrumental noise and stellar variability can masquerade as spectral features, demanding repeated observations. Historical lessons, including past claims that later proved premature, reinforce the need for restraint. In planetary science, the cost of misinterpretation is not only scientific error, but erosion of credibility. Biosignature research advances through patience. Molecules in alien skies do not speak plainly. They require careful translation grounded in physics and chemistry. The goal is not merely to detect intriguing compounds, but to situate them within coherent planetary narratives. Only when disparate strands of evidence align does the possibility of life rise above alternative explanations, emerging gradually from a field of plausible but uncertain signals. Long before telescopes could separate the atmospheres of distant planets from their stars, another approach turned outward with quiet anticipation. Instead of searching for chemistry, scientists began listening. Large radio dishes swept slowly across the sky, tuned to frequencies thought to be natural meeting points between physics and intention. The expectation was modest, rooted not in imagery, but in the possibility that advanced civilizations, if they existed, might use electromagnetic signals to bridge the vast distances between stars. Radio waves became the earliest focus because they travel efficiently through interstellar space with relatively little absorption. Specific frequencies, such as the narrow band near the hydrogen line at 1,000 420 megahertz, were considered promising, situated between background cosmic noise and atmospheric interference. Arrays of antennas monitored these regions for patterns that differed from the random static of natural sources. A narrow, repeating signal would stand out sharply against the hiss of the universe, a tone too precise to be explained by pulsars or quasars. Over time, optical searches joined the effort. Powerful lasers can emit brief flashes brighter than entire stars for fractions of a second, and such pulses, if directed intentionally, might carry information across light years. Sensitive detectors now scan for transient bursts of coherent light, distinguishing them from cosmic rays and instrumental artifacts. The logic remains consistent. An artificial signal would exhibit structure, regularity, or spectral properties unlikely to arise from astrophysical processes alone. Despite decades of observation, no confirmed signal has persisted beyond scrutiny. A few anomalous events have appeared, then faded or resisted repetition. Each time, further analysis has traced the source to terrestrial interference, satellite reflections, or natural cosmic phenomena. The sky returns to its background murmur, steady and unresolved. Yet, absence of detection does not equate to absence of transmitters. The search has examined only a fraction of the electromagnetic spectrum and a limited portion of the sky at any given moment. Sensitivity thresholds restrict how faint a signal can be before it blends into noise. Civilizations, if they exist, may not broadcast continuously or at frequencies currently monitored. They might communicate through methods not yet anticipated or exist in epochs that do not overlap with our own technological window. The scale of space imposes additional constraints. Signals weaken with distance, according to the inverse square law, demanding immense energy for transmission across thousands of light years. Even with large receiving arrays, faint emissions from distant sources may remain undetectable against cosmic background radiation. Meanwhile, Earth's own radio leakage into space is modest and gradually decreasing as communication technologies shift toward less radiative methods. The listening continues, refined by improved algorithms and expanding instrumentation. Each survey adds incremental coverage, mapping regions of possibility rather than emptying them. Silence, measured carefully, becomes data in itself, shaping probability estimates and informing future strategies. Within the narrow slices of frequency and time explored so far, no unmistakable message has emerged. But the vast majority of cosmic bandwidth remains unexamined, stretching outward, beyond the quiet intervals we have already heard. Even if the galaxy were scattered with thinking beings, the architecture of space itself would conspire to keep them apart. Light, though swift by any terrestrial measure, requires years to cross the gulf between neighboring stars and tens of thousands to traverse the span of the Milky Way. Signals that begin as focused beams disperse as they travel, their strength diminishing according to the inverse square law until they merge with background radiation. A transmission bold at its source becomes fragile at distance, buried within cosmic noise long before it reaches most potential listeners. Energy can compensate only to a degree. To remain detectable across thousands of light years, a signal must be sustained with enormous power or directed with extraordinary precision. Both demand resources and intent. Civilizations may choose efficiency over broadcast, reserving energy for survival rather than interstellar outreach. Even if they transmit, the alignment between sender and receiver must coincide in space and orientation, an additional constraint layered atop distance. Time introduces a deeper limitation. Technological capability may occupy only a brief chapter within a species' existence. On Earth, radio communication has been present for little more than a century, a thin slice against the backdrop of billions of years of biological evolution. If other civilizations follow similarly transient trajectories, their detectable phases could flicker on and off across cosmic history. The probability that two societies develop communication technology simultaneously and within range of one another becomes narrower than raw population estimates might suggest. Galactic history spans more than 13 billion years. Stars form and die, planets cool, atmospheres evolve. A civilization that transmitted signals 1 million years ago would have done so long before humans began listening. Conversely, a society emerging far in the future may find only the faint residue of our own brief broadcasts drifting outward. Overlapping timelines may be rare not because intelligence is scarce, but because synchronized development across astronomical scales is improbable. This temporal mismatch alters the question from how advanced technology must be to how precisely it must align. A modest transmission received at the right epoch conveys more than the most powerful signal sent into silence. Timing governs detectability more than sheer capability. Even perfect instruments cannot intercept a message that was never contemporaneous. These considerations temper expectations without resolving uncertainty. The galaxy's vastness stretches not only across distance, but across eras. Signals fade, civilizations evolve, and windows of opportunity open and close. The scale problem operates quietly, yet relentlessly, shaping probabilities in ways that resist intuition. Between the weakening of waves over space and the brevity of technological lifespans, communication depends on coincidence as much as innovation, situating the search within a framework where alignment of time and distance may prove the rarest factor of all. In quiet offices and observatories, calculations sometimes outpace evidence. When astronomers multiply the number of stars by the fraction that host planets, then estimate how many of those worlds might support life, the resulting figures suggest abundance. Even conservative assumptions yield large numbers. Against this expectation stands a simple observation: the sky has offered no unambiguous sign of technological activity. The contrast between statistical optimism and empirical silence is often referred to as the Fermi paradox, though it is less a paradox than a tension between projection and measurement. The reasoning begins with scale. Hundreds of billions of stars populate our galaxy, many older than the Sun. If life emerges readily, and sometimes evolves intelligence, then over cosmic time, there should have been ample opportunity for civilizations to arise, expand, and leave detectable traces. Such traces might include engineered megastructures, altered planetary atmospheres, or deliberate transmissions. Yet, careful searches for anomalies consistent with large-scale engineering have yielded none that withstand scrutiny. Radio surveys have not revealed persistent artificial signals. Infrared observations have not confirmed starlight reprocessed by vast technological arrays. Several explanations have been proposed, each addressing a different assumption. Perhaps the emergence of intelligence is exceedingly rare, dependent on improbable evolutionary steps. Perhaps technological societies tend to extinguish themselves or retreat from detectability before achieving interstellar presence. It is possible that expansion across the galaxy proceeds far more slowly than imagination suggests, constrained by energy costs and physics. Another possibility holds that advanced civilizations exist but choose not to broadcast, or that their activities are subtle beyond current detection limits. None of these interpretations commands decisive evidence. Each relies on variables that remain largely unconstrained. The probability of abiogenesis on a suitable planet is not yet known. The average lifespan of a technological civilization cannot be inferred from a single example. Estimates of colonization timescales depend on sociological assumptions layered atop physical constraints. Even the definition of detectable activity evolves as instrumentation improves. The unease arises from the gap itself. High numerical estimates coexist with persistent quiet. Scientific caution prevents premature conclusions, yet the absence of confirmation over decades of searching weighs on theoretical models. If life is common but intelligence scarce, the galaxy may teem with microbial ecosystems yet remain technologically silent. If intelligence is common but transient, the chance of overlap in time diminishes sharply. If expansion is rare or undesirable, then absence reflects choice rather than impossibility. Revisiting the paradox carefully reveals that it is built upon uncertainties more than contradictions. Probability distributions span wide ranges, and observational coverage remains incomplete. The apparent mismatch between expectation and evidence may narrow as parameters become better constrained. For now, the question endures without resolution, suspended between vast potential and measured quiet, leaving scientists attentive to both the mathematics of possibility and the disciplined patience of observation. Not all planets are built from the same quiet coincidences. Earth's long record of biological continuity rests on a network of physical conditions that operate in concert, each subtle on its own, yet collectively profound. Among them is the presence of a large moon, unusually massive relative to its host planet. Its gravitational pull steadies Earth's axial tilt, limiting extreme variations over geological time. Without such stabilization, simulations suggest that a planet's obliquity could wander dramatically, swinging climate between severe states that challenge persistent habitability. Beneath the surface, tectonic plates drift slowly across a viscous mantle, recycling crust and regulating atmospheric composition. Through the carbon silicate cycle, carbon dioxide is drawn down by weathering, buried in sediment, and later returned through volcanic outgassing. This circulation moderates the greenhouse effect across millions of years, preventing runaway heating or irreversible freezing under normal stellar evolution. Plate tectonics also reshapes continents, diversifies ecological niches, and maintains geochemical flux between interior and surface. Encasing the planet, a magnetic field generated by convection within the molten outer core deflects charged particles streaming from the sun. This magnetosphere reduces atmospheric erosion, shielding lighter molecules from being stripped away over time. While not an absolute barrier, it preserves the integrity of the atmosphere and protects surface chemistry from intense radiation. Worlds lacking similar protection may experience gradual thinning of air, altering pressure and surface temperature in ways that destabilize liquid water. Climate stability emerges from the interplay of these mechanisms. Feedback loops between oceans, atmosphere, and biosphere contribute to resilience. Clouds reflect sunlight. Ice increases planetary albedo when temperatures fall, and living systems modify gas concentrations. None of these processes alone guarantees equilibrium, but together they buffer fluctuations that might otherwise escalate. Earth has endured ice ages, asteroid impacts, and volcanic winters, yet has avoided permanent transformation into a Venus-like furnace or a Mars-like desert. The rare Earth hypothesis proposes that this particular combination of features may be uncommon. A large stabilizing moon likely formed through a specific type of collision. Sustained plate tectonics may require a delicate balance of internal heat and water content. A long-lived magnetic field depends on core composition and rotational dynamics. The coincidence of these conditions around a star of suitable stability may narrow the frequency of planets capable of supporting complex life for billions of years. Current exoplanet observations cannot yet measure tectonic activity or magnetic shielding directly, nor can they reliably determine axial stability without extended monitoring. As a result, estimates of how often Earth-like conditions truly converge remain uncertain. The rare Earth perspective does not assert uniqueness with certainty, but it highlights how multiple independent factors might need to align. Habitability, under this view, becomes a product of layered contingencies rather than simple orbital placement, shaped by internal structure as much as by distance from a star. Across the long chain from lifeless chemistry to technological civilization, there may exist a narrow gate through which very few worlds pass. The Great Filter hypothesis proposes that somewhere along this progression, one step is so improbable that it sharply reduces the number of civilizations capable of reaching detectable stages. The location of that bottleneck remains uncertain, yet its implications extend quietly through every estimate of cosmic life. The sequence from simple molecules to self-replicating systems, from single cells to complex multicellular organisms, from intelligence to technology, contains many transitions. On Earth, some of these stages unfolded rapidly, others required billions of years. The emergence of eukaryotic cells with internal structures, for example, appears to have been a rare event in evolutionary history. Similarly, the rise of tool-using, technologically inclined intelligence occurred in only one lineage. Any of these milestones could represent an unlikely threshold, one that most biospheres never cross. If the Great Filter lies early in the chain, perhaps at the origin of life itself, then Earth may have already cleared the most formidable barrier. In that case, simple organisms could be abundant, while complex life remains scarce. Conversely, if the most improbable step lies ahead, perhaps in the long-term survival of technological societies, then civilizations might frequently arise only to fade before spreading widely. The uncertainty surrounding this placement shapes how scientists interpret silence. It reframes absence not merely as lack of evidence, but as potential evidence of rarity at a particular stage. The concept carries an uneasy weight because it intersects with humanity's own trajectory. If the most difficult transition has already occurred in our past, then our existence is the result of a sequence of improbable successes. If it lies in our future, then survival beyond certain technological or environmental thresholds may prove exceptionally challenging. The hypothesis does not specify causes. It only points to statistical thinning somewhere along the path. Despite its influence in discussion, the Great Filter remains speculative. It rests on broad estimates of probabilities that are still largely unconstrained. The rate at which life begins on suitable planets, the frequency with which complex cells arise, the likelihood of intelligence persisting over geological timescales, all remain subjects of active research. With only one confirmed example of a biosphere progressing to technology, statistical inference is limited. What the hypothesis offers is a framework for organizing uncertainty. It acknowledges that the gulf between microbial life and galactic presence may contain stages of extraordinary improbability. It does not determine which stage qualifies, nor does it assign inevitability. Until additional biospheres are discovered and characterized, the filter's position cannot be measured directly. It remains a conceptual lens, applied cautiously, reminding observers that somewhere within the sequence, from chemistry to consciousness, rarity may exert a decisive influence. For most of Earth's history, the planet was inhabited exclusively by organisms that neither built tools nor contemplated their surroundings. Microbial life dominated oceans and soils for billions of years, refining metabolism, adapting to shifting climates, and reshaping the atmosphere without ever developing nervous systems. Complex ecosystems flourished long before any species learned to harness fire or transmit radio waves. In this context, intelligence appears not as an inevitable culmination, but as a recent and localized experiment. Cognitive capacity demands significant biological investment. Large brains require disproportionate energy, constant oxygen, and prolonged developmental periods. In humans, the brain accounts for roughly 2% of body mass, yet consumes about 20% of resting metabolic energy. Such expenditure must be offset by ecological advantages. Social coordination, problem solving, and tool use can enhance survival under certain conditions, yet these benefits emerge only when environmental pressures favor flexibility over specialization. In stable niches, where adaptation through physical traits suffices, elaborate cognition may confer little additional value. Evolution operates through incremental changes shaped by immediate reproductive success rather than long term foresight. Traits that improve survival within a given environment proliferate. Those that impose costs without compensating advantages fade. Intelligence, particularly of a technological kind, may require a rare convergence of factors. Fluctuating climates that reward adaptability, social structures that amplify learning, and anatomical features capable of manipulating objects with precision. Absent this convergence, life can persist and diversify without approaching self awareness. Even among multicellular organisms, advanced cognition is unevenly distributed. Many successful lineages, from insects to plants, rely on efficient behavioral strategies encoded through instinct rather than reasoning. These organisms thrive across continents and oceans, demonstrating that intelligence is not a prerequisite for ecological dominance. Natural selection does not prioritize contemplation or abstract thought unless they enhance reproductive outcomes. Technological intelligence introduces additional complexity. It enables manipulation of environments at unprecedented scales, altering ecosystems and atmospheric chemistry within short time spans. Such capacity carries risks alongside advantages. The same tools that provide security and comfort can destabilize planetary systems if misapplied. From an evolutionary perspective, a species capable of rapid environmental modification must also develop mechanisms for restraint and cooperation, traits that are themselves contingent on social evolution. The rarity of advanced intelligence may therefore reflect cumulative improbabilities rather than simple scarcity of life. Each stage, from the emergence of neurons to the development of symbolic language, adds layers of contingency. Microbial biospheres may be common, sustained by chemical cycles that operate reliably for billions of years. Complex cognition, by contrast, depends on structural and ecological thresholds that may seldom align. Intelligence is remarkable, yet it is not mandatory for persistence. Life can endure in forms that never gaze upward or question their origins. In that sense, awareness may represent a narrow branch rather than a universal trajectory, an outcome shaped by specific planetary histories rather than a predetermined endpoint of evolution. Human understanding of life is shaped by a single example. Every definition, every instrument, every model has been calibrated against the chemistry of one biosphere. Carbon chains, liquid water, oxygen rich atmospheres, cellular membranes composed of lipids. All of these reflect Earth's solution to the problem of sustaining organized complexity. Yet, the universe is not obligated to repeat this pattern. Carbon is favored because it forms stable, versatile bonds, allowing intricate molecular architectures. However, silicon also forms four bonds and can assemble extended structures under certain conditions. In environments where temperatures, pressures, or solvent chemistry differ from Earth's, alternative backbones for complex molecules are not impossible in principle. Whether such chemistries can support replication and evolution remains uncertain, yet their mere plausibility broadens the search beyond strict terrestrial templates. Oxygen, often treated as a signature of advanced life, is not required for metabolism. For most of Earth's early history, organisms thrived in anoxic oceans, relying on fermentation or chemical gradients rather than oxidative respiration. Even today, entire ecosystems exist without free oxygen, drawing energy from sulfur or iron compounds. A planet devoid of atmospheric oxygen could host a biosphere invisible to sensors, tuned to modern Earth analogs. Metabolic rate further complicates detection. Life need not operate on rapid, observable timescales. In extreme environments on our own planet, some microbes divide only once in hundreds or thousands of years, maintaining slow but persistent chemical activity. On colder worlds, where reaction rates are reduced, living systems might function at rhythms that appear static over short observational windows. Instruments designed to detect dynamic fluxes may overlook processes unfolding gradually. Detection limits impose practical boundaries. Telescopes measure integrated light from entire planets, averaging signals across continents and oceans. A sparse biosphere, confined to subsurface niches or thin microbial mats, may not alter atmospheric composition sufficiently to register from afar. Even surface reflectance patterns, sometimes proposed as indicators of vegetation, depend on large-scale coverage. Subtle or patchy life would blend into geological background. Observer bias adds another layer. Scientists tend to prioritize molecules and conditions familiar from Earth's history, constructing search strategies around known pathways. While this approach is methodologically sound, it risks narrowing perception. Unanticipated chemistries could produce atmospheric signatures that are dismissed as noise or misinterpreted as purely abiotic phenomena. The history of science contains examples where phenomena remained unrecognized because they did not fit prevailing frameworks. The possibility that life might exist in forms currently undetectable does not imply that detection is futile. Rather, it underscores the importance of expanding models and refining sensitivity. As instrumentation advances, spectra become more detailed, and laboratory experiments explore alternative chemistries. The conceptual window widens. Life could be abundant yet subtle, operating beyond current thresholds of recognition. Until additional biospheres are observed directly, the boundaries of detectability remain provisional, shaped as much by human expectation as by planetary reality. Between the stars lies a distance so vast that even light requires years to cross it. Proposals for interstellar travel often begin with velocities approaching a significant fraction of that speed, yet the energy required to accelerate a spacecraft to even 10% of light speed is immense. The kinetic energy scales with the square of velocity, meaning each incremental increase demands disproportionately greater power. For a vessel large enough to sustain biological life, the fuel mass and propulsion systems would extend far beyond current engineering capabilities. Even if such propulsion were achieved, timescales remain formidable. The nearest star system, Alpha Centauri, is more than 4 light years away. At 10% of light speed, a journey would take over 40 years, not accounting for acceleration and deceleration. Slower velocities stretch travel into centuries. Human lifespans do not naturally align with these durations, and sustaining closed ecological systems over generations introduces complexities not yet resolved. Mechanical systems must function without resupply across environments where repair opportunities are limited to what is carried aboard. Radiation exposure compounds these challenges. Outside the protective cocoon of a planetary magnetic field and atmosphere, high energy particles permeate space. Galactic cosmic rays and solar particle events can damage electronics and biological tissue alike. Shielding sufficient to reduce radiation to safe levels adds mass, which in turn increases propulsion demands. Even small dust grains encountered at relativistic speeds carry destructive potential, impacting hulls with energies comparable to explosive projectiles. These constraints suggest that spontaneous visitation by crewed vessels is improbable. The energetic cost alone discourages large scale travel, and the engineering requirements impose additional barriers. Civilizations may weigh these factors and conclude that sustained interstellar migration offers diminishing returns compared to local optimization. Distance acts not merely as separation, but as deterrent. Uncrewed probes, however, alter the equation. Robotic systems can tolerate longer travel times and harsher conditions. Without the need to sustain life support, mass requirements decrease, reducing propulsion energy. Autonomous navigation and artificial intelligence allow probes to operate with minimal real-time oversight, transmitting data back across decades. Concepts such as solar sails, propelled by intense laser arrays, envision accelerating lightweight spacecraft to significant fractions of light speed without carrying traditional fuel. Even so, probes face communication delays and limited payload capacity. Information transmission weakens over distance, subject to the same inverse square constraints that challenge detection of alien signals. Yet compared to transporting biological organisms, dispatching instruments appears more achievable within known physics. Interstellar travel does not resolve the silence discussed earlier. The difficulties inherent in crossing stellar distances imply that physical presence across the galaxy would be rare and slow. Communication, observation, and indirect study remain more practical than migration. The structure of space itself shapes the strategies available to any technological society, favoring patience and remote sensing over rapid expansion. High above Earth's atmosphere, positioned near the Sun-Earth L2 point, the James Webb Space Telescope unfolds its segmented mirror and sunshield, turning its gold-coated surface toward faint infrared light that has traveled for years before arrival. Its vantage allows it to observe wavelengths absorbed by water vapor and carbon dioxide in our own atmosphere, granting access to spectral regions previously obscured. In doing so, it refines rather than replaces earlier efforts, extending sensitivity into domains where subtle atmospheric features become measurable. Webb's primary strength lies in its ability to perform high-precision spectroscopy of transiting exoplanets. As starlight filters through distant atmospheres, the telescope detects minute changes in infrared absorption with unprecedented resolution. Molecules such as water vapor, carbon dioxide, methane, and sulfur dioxide can now be constrained with greater confidence, even on smaller planets. Temperature profiles and cloud structures emerge from careful modeling of emission spectra during secondary eclipses. The datasets are richer, the uncertainties narrower, yet improved sensitivity does not equate to immediate revelation. The atmospheres most readily studied remain those of large, close orbiting planets that produce stronger signals. Rocky Earth sized worlds in temperate orbits generate far subtler imprints, challenging even Webb's capabilities. Observing them requires repeated transits, careful calibration, and extensive integration time. Each planetary system demands patience, and telescope scheduling must balance many competing scientific goals. Better data reshape probability distributions rather than delivering definitive conclusions overnight. For instance, detection of carbon dioxide in an exoplanet atmosphere constrains models of climate and composition, but it does not by itself indicate biology. Establishing chemical disequilibrium requires simultaneous measurement of multiple gases, each with sufficient signal to rule out abiotic pathways. Even then, interpretation must consider stellar radiation, planetary mass, and evolutionary history. The pace of discovery reflects the scale of the task. Light from these worlds arrives faint and filtered through layers of uncertainty. Instrumental noise must be characterized, stellar variability accounted for, and alternative hypotheses tested. Scientific claims, particularly those concerning life, require rigorous thresholds. A true detection would likely present as a persistent, reproducible spectral signature across multiple observing cycles, accompanied by models demonstrating that non biological processes fail to account for the observed combination of gases. It would withstand independent analysis and refinement, gradually shifting consensus rather than erupting in a single dramatic announcement. Webb has expanded the horizon of atmospheric characterization, transforming blurred outlines into structured spectra. It has not solved the question of life beyond Earth, nor was it designed to do so in isolation. Instead, it provides sharper tools, enabling future observatories to build upon its foundation. Discovery remains incremental, grounded in accumulation and verification. Each spectrum analyzed contributes to a growing archive, drawing the contours of alien atmospheres with increasing clarity while preserving the discipline that has guided the search from its beginning. While telescopes gather light from afar, certain questions require movement, trajectories calculated years in advance, and spacecraft assembled piece by piece under cleanroom ceilings. Two missions, now in development, embody this shift from distant inference to direct encounter, each aimed at worlds where liquid reservoirs may persist beneath alien skies. Europa Clipper will orbit Jupiter and conduct dozens of close flybys of Europa, repeatedly sweeping through its radiation bathed environment. Rather than landing immediately, the spacecraft is designed to map the moon's surface in high resolution, measure the thickness of its ice shell, and analyze the chemistry of material lofted from cracks. Ice penetrating radar will probe beneath the crust, searching for pockets of brine and pathways that connect surface fractures to the deeper ocean. Spectrometers will examine salts and organic compounds distributed along ridges and chaotic terrains, building a layered understanding of surface exchange with the hidden sea below. Dragonfly, by contrast, will descend through Titan's dense atmosphere and travel from site to site using rotors, functioning as a nuclear-powered rotorcraft. Its mobility allows it to sample diverse environments, from ancient impact craters to organic rich dunes. Instruments aboard Dragonfly will analyze surface composition, atmospheric chemistry, and energy gradients that may illuminate prebiotic processes. Unlike orbiters that rely solely on remote sensing, Dragonfly will touch the ground, drilling and scooping material to assess molecular complexity directly. Sampling strategies in these missions reflect lessons learned from earlier explorations. Multiple instruments provide redundancy, cross validating measurements to reduce ambiguity. Surface composition, isotopic ratios, and mineral contexts are examined together rather than in isolation. On Europa, identifying regions where ocean derived material reaches the surface could narrow future landing sites for more ambitious probes. On Titan, assessing chemical pathways across varied terrains will clarify how organic molecules accumulate and transform over time. Neither mission expects to confirm life outright. Instead, both seek to characterize habitability with greater precision, refining models of internal structure, chemical gradients, and energy availability. By constraining these variables, scientists reduce uncertainty about whether sustained biology could plausibly arise or persist in such environments. The timelines involved underscore the necessity of patience. Years separate launch from arrival, and additional years pass before datasets are fully analyzed. Radiation environments must be navigated carefully, and communication delays impose methodical pacing. Discovery in this context unfolds gradually, shaped by incremental measurements rather than sudden revelations. Ocean worlds occupy a central place in astrobiological planning because they combine liquid water with internal energy sources. Missions directed toward them acknowledge that some of the most promising environments may be concealed beneath ice or hydrocarbon haze. Progress depends on deliberate exploration, accepting that understanding distant seas requires steady accumulation of evidence carried across millions of kilometers by instruments designed for endurance and precision. Scientific history carries moments of excitement that later required revision. In the late 19th century, linear markings glimpsed on Mars through telescopes were interpreted as canals, suggesting engineered waterways across a neighboring world. Decades later, higher resolution observations revealed natural geological features instead. In the 20th century, a meteorite discovered in Antarctica was proposed to contain microfossils from ancient Martian life, an announcement that stirred global attention. Subsequent analyses cast doubt on the biological interpretation, favoring non biological chemical processes. These episodes remain instructive, not as failures of curiosity, but as reminders of how easily desire for discovery can outpace available evidence. Because of this history, modern astrobiology operates under a principle often summarized as requiring extraordinary evidence for extraordinary claims. The discovery of life beyond Earth would alter biology, philosophy, and planetary science simultaneously. It would demand confirmation at multiple levels, from chemical signatures to contextual analysis. Single data points rarely suffice. Observations must be repeatable, reproducible by independent teams, and resilient against alternative explanations grounded in physics and chemistry. Reputation and credibility are intertwined with this caution. Scientific institutions and missions depend on public trust and sustained funding. Premature claims that later collapse can erode confidence, not only in individual researchers, but in broader programs. As a result, investigators scrutinize anomalies carefully, inviting critique before drawing far-reaching conclusions. Peer review, statistical validation, and cross-instrument comparison form layers of verification designed to reduce error. Skepticism within science does not represent dismissal, but protection. It shields interpretation from confirmation bias and encourages examination of mundane explanations before invoking rare phenomena. In planetary atmospheres, unexpected spectral lines prompt rigorous analysis of instrument calibration, stellar interference, and modeling assumptions before being attributed to biological sources. In surface samples, unusual structures are tested against geological processes capable of producing similar forms. This deliberate pacing can appear slow, especially in contrast to the speed of news cycles. Datasets may circulate quietly among specialists for months or years before publication. Conferences often feature debates over interpretation rather than announcements of certainty. Such restraint is embedded in methodology rather than imposed externally. Each claim must withstand scrutiny, not only from its proponents, but from those prepared to challenge it. The refusal to rush does not indicate lack of ambition. Instead, it reflects an understanding that conclusions about life beyond Earth carry lasting consequences. A verified detection would enter textbooks and reshape research priorities for generations. Protecting that moment from error ensures that when consensus forms, it rests upon durable foundations. Caution thus functions not as obstacle, but as safeguard, guiding inquiry through complexity while maintaining the integrity that allows scientific knowledge to endure. Stripped of conjecture and restrained to observation, several statements can be made with confidence. The elements required for life, as understood on Earth, are not rare curiosities. Hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur arise readily from stellar nucleosynthesis and are distributed throughout galaxies. Spectroscopic surveys of interstellar clouds reveal organic molecules drifting between stars, including amino acid precursors and complex carbon chains. The building blocks of biochemistry assemble naturally in space, long before planets form. Water, a crucial solvent for terrestrial life, is abundant as well. It condenses on dust grains in molecular clouds and becomes incorporated into comets, asteroids, and planetary bodies during formation. Observations have identified water vapor in protoplanetary disks and frozen reservoirs within our own solar system. Liquid water depends on temperature and pressure, yet environments capable of sustaining it have been confirmed beyond Earth, whether in subsurface oceans or ancient river valleys etched into rock. Planets themselves are common. Thousands orbit distant stars, and statistical analyses indicate that such worlds outnumber stars in the observable universe. Among them are rocky planets within orbital distances compatible with moderate surface temperatures, as well as icy moons warmed internally by gravitational interactions. The physical conditions that can support chemical complexity appear to recur across diverse systems. Habitable environments, defined by the potential to maintain liquid solvents and energy gradients, demonstrably exist beyond our planet. Life on Earth demonstrates resilience across extremes once thought prohibitive. Microorganisms persist in acidic lakes, beneath kilometers of ice, within deep rock formations, and in radiation-exposed deserts. Metabolic pathways utilize chemical sources independent of sunlight. These empirical findings broaden the range of conditions under which biology can operate. They also caution against narrow assumptions about where life might endure elsewhere. Despite these encouraging factors, no confirmed detection of extraterrestrial life has been made. No atmospheric spectrum has yielded a biosignature immune to non-biological explanation. No rover has uncovered fossilized microstructures that withstand exhaustive scrutiny. No radio telescope has recorded a signal unequivocally attributed to intelligent origin. The observational record remains silent on this decisive point. These conclusions form a stable boundary between evidence and inference. Ingredients are widespread, planets plentiful, and environments capable of supporting complex chemistry demonstrably present. Life thrives under varied conditions on Earth, expanding the theoretical landscape of habitability. Yet empirical confirmation beyond our world has not occurred. The search continues within these constraints, guided by data rather than assumption, charting what is known with clarity while acknowledging what remains unverified. Seen from a distance measured in light years, Earth would appear as a faint blue point orbiting an unremarkable star. Its oceans would not be visible as waves, its forests not as trees, but as subtle shifts in reflected light and atmospheric chemistry. The search for life beyond our world has sharpened the awareness of how unusual this combination appears, not because rarity is proven, but because confirmation elsewhere has yet to arrive. Liquid water spans the majority of Earth's surface, stabilized within a narrow range of temperature and pressure that has persisted for billions of years. Atmosphere and ocean exchange gases in a dynamic equilibrium, supporting complex webs of organisms that modify their environment even as they depend upon it. When compared with neighboring planets that lost their seas or never sustained them, Earth's continuity resembles an oasis within a broader desert of hostile conditions. This perspective arises not from sentiment, but from comparative planetary science. Ecosystems here are resilient, yet they operate within constraints. Biodiversity depends on stable climate patterns, nutrient cycles, and energy flows anchored in solar input. Disruptions in these systems ripple outward, altering habitats and species distributions. Geological history records multiple mass extinctions, events that reshaped life's trajectory through volcanic activity, asteroid impacts, and atmospheric shifts. Each extinction underscores that habitability at planetary scale does not guarantee security for particular lineages. Understanding other worlds clarifies how delicate balance can be. Atmospheric erosion, runaway greenhouse warming, and loss of internal dynamo activity illustrate pathways by which planets diverge from clement states. Against this backdrop, Earth's continued support of complex life acquires additional context. Stability emerges not as default, but as maintained equilibrium, influenced by internal processes and external forcing. The search also reframes responsibility. If habitable conditions are uncommon or fleeting, then the stewardship of a functioning biosphere becomes consequential. Human activity now alters atmospheric composition and surface ecosystems at rates measurable within decades. In planetary terms, such changes are abrupt. Recognizing Earth as part of a broader spectrum of worlds highlights the rarity of environments where biology flourishes at scale. This reframing does not rely on asserting uniqueness with certainty. It rests on comparison and evidence, on the observable contrast between Earth's living surface and the barren landscapes surveyed thus far. As telescopes examine distant atmospheres and probes sample icy moons, each negative result or ambiguous signal reinforces how singular our confirmed example remains. The blue point persists, luminous against surrounding darkness, not as a guaranteed constant, but as a contingent outcome sustained through intertwined geological and biological processes that merit both study and care. In laboratories, observatories, and quiet offices where data accumulate line by line, the absence of confirmation becomes its own presence. Years of measurements, spectra analyzed, signals filtered, and samples tested have not yet yielded the unmistakable signature of life beyond Earth. The silence is not theatrical or dramatic. It is steady, patient, woven through decades of careful inquiry. There is awe in the scale of what has been examined. Thousands of planets catalogued, atmospheric compositions inferred, icy moons mapped in detail, instruments sensitive enough to detect trace gases in distant worlds now operate routinely. Yet alongside this expansion of knowledge remains an open space where definitive discovery might have been expected. The contrast between technological sophistication and unanswered questions carries a subtle weight. Scientific culture meets this weight with humility. The vastness of the cosmos exceeds individual careers and even generations of research. Each null result refines models, narrows parameter spaces, and reshapes probability estimates, but none compels immediate resolution. Uncertainty persists, not because of neglect, but because reality often resists simple narratives. Biological emergence involves chemistry, geology, and time interwoven in complex ways that may not repeat predictably. The endurance of uncertainty has emotional dimensions, though rarely stated overtly. Many researchers entered the field motivated by curiosity about companionship in the universe. The hope for detection coexists with disciplined restraint. Data must speak before conclusions form. When results remain ambiguous or negative, the commitment to continue reflects dedication to method rather than attachment to outcome. Mystery, in this context, is not failure. It is an accurate reflection of incomplete information. The scientific method does not promise rapid closure. It promises gradual approximation toward truth. Accepting this boundary allows exploration to continue without distortion. Silence becomes a datum, one that informs models of rarity, distribution, and detectability. At the same time, the absence of confirmed signals highlights the uniqueness of our own biosphere as the only verified example. This fact carries both intellectual intrigue and existential reflection. The cosmos does not yet reveal whether life is abundant or scarce, whether intelligence is common or fleeting. It offers instead a canvas on which evidence accumulates slowly. The emotional cost, if it can be called that, lies in sustaining curiosity without resolution. Researchers analyze faint traces, publish incremental findings, and recalibrate instruments, aware that definitive answers may lie beyond immediate reach. Yet this sustained effort embodies a particular strength: the willingness to dwell within uncertainty, to treat mystery as legitimate rather than intolerable, preserves the integrity of inquiry. In that quiet persistence, the search continues, measured not by dramatic breakthroughs, but by careful accumulation of understanding within a universe that remains, for now, largely silent. At this point in the search, the most responsible statement is not a declaration, but a boundary. There are measurements, models, probabilities, and carefully constrained interpretations. There are also gaps that remain unfilled, variables not yet sampled, environments not yet reached. The honest position rests between what has been established and what has not. Open questions define the landscape. How often does chemistry transition into biology? Under what planetary conditions does simple life persist long enough to diversify? Whether intelligence is an expected outcome of evolution or a rare branch that seldom extends far, these inquiries are framed within data, yet none has crossed the threshold into certainty. Each depends on processes that may vary across worlds in ways still poorly understood. Competing hypotheses coexist because evidence accommodates more than one interpretation. Some models suggest that microbial life could be widespread, hidden in oceans beneath ice, or in atmospheres we have yet to probe deeply. Others propose that while basic chemistry is common, the step towards self sustaining replication may be exceptionally improbable. Statistical arguments draw upon exoplanet frequencies, stellar lifetimes, and geological constraints, producing ranges rather than precise numbers. Theoretical work continues to refine these possibilities without eliminating ambiguity. No final answers have emerged despite decades of targeted investigation. Atmospheric spectra provide hints but not proof. Surface missions yield context without decisive fossils. Radio surveys scan narrow bands of frequency while acknowledging that technological civilizations, if they exist, may not transmit in predictable ways. Each method narrows uncertainty incrementally. None has resolved it. Certainty would require evidence that withstands alternative explanations and independent scrutiny. A confirmed biosignature would need to demonstrate chemical disequilibrium incompatible with known abiotic pathways observed consistently across multiple measurements. Direct detection of organisms would require samples unambiguously biological in origin, embedded in planetary context. Such standards are exacting because the implications are vast. Premature confidence would risk error at a scale difficult to correct. The most honest stance, therefore, is one of disciplined openness. It accepts the plausibility of life elsewhere while acknowledging that plausibility differs from proof. It recognizes that current instruments sample only a fraction of planetary diversity, and that time horizons for exploration extend far beyond individual projects. This position values patience as much as possibility. Within that restraint lies strength. Science advances by reducing uncertainty through accumulation, not by leaping beyond evidence. Remaining questions are not signs of failure, but markers of progress yet to be made. In holding space for multiple hypotheses without elevating any prematurely, inquiry preserves its integrity. The universe, vast and intricate, has not delivered a final verdict. Until it does, the honest scientific position remains steady, grounded in data, attentive to limits, and prepared to revise conclusions when new evidence arrives. Long before results are finalized or headlines written, the act of searching reshapes understanding. Telescopes are calibrated, spacecraft assembled, algorithms refined, and with each step, the boundaries of knowledge expand slightly outward. The search for life beyond Earth proceeds without guarantees, yet it generates insight regardless of outcome. Negative results constrain models, sharpen detection methods, and clarify which environments are less promising than once believed. In narrowing uncertainty, science advances even when confirmation remains absent. Curiosity lies at the center of this persistence. Across cultures and centuries, humans have turned their gaze upward, constructing narratives to explain lights in the sky. Modern inquiry replaces myth with measurement, but the impulse is continuous. The desire to understand origins, distribution, and possibility propels research programs that span decades. It sustains collaboration across nations and disciplines, linking astronomy, chemistry, geology, and biology into a shared endeavor. The effort continues because each new instrument deepens context. Exoplanet catalogs reveal diversity beyond early expectations, showing worlds that challenge pre-existing categories. Studies of planetary atmospheres refine climate theories applicable to Earth itself. Investigations of icy moons inform geophysics and oceanography. Even without discovering extraterrestrial organisms, the search strengthens foundational science. It enriches models of planetary evolution and clarifies the processes that shape habitable environments. Silence, too, carries instruction. The absence of detected signals influences probability estimates and theoretical frameworks. If intelligent civilizations are not readily observed, this informs assumptions about technological longevity or detectability. If biosignatures remain elusive despite improved sensitivity, chemical pathways once considered obvious may require reassessment. Each quiet dataset contributes to an evolving picture, subtle yet cumulative. The search fosters technological innovation as well. Advanced detectors, data processing techniques, and materials designed for deep space missions often find applications beyond astronomy. The infrastructure built to probe distant worlds reinforces scientific capability more broadly. Knowledge gained in pursuit of one question cascades into adjacent fields. There is also value in confronting vastness directly. Engaging with cosmic scale situates humanity within a larger context, encouraging long term thinking over immediate horizons. Research agendas extending decades into the future cultivate patience and cooperation, qualities essential for addressing challenges closer to home. Ultimately, the significance of the search lies not solely in potential discovery, but in disciplined exploration itself. It embodies a commitment to evidence over assumption and to inquiry over speculation. Whether life proves abundant or rare, the path taken toward understanding refines perception. In listening carefully to the universe, even when it offers no clear reply, science accumulates clarity. The quiet becomes part of the record, guiding future questions and sustaining the momentum of exploration. At the edge of our measurements, where spectra thin into noise and signals dissolve into background radiation, the universe offers no definitive reply. Decades of searching have refined instruments and expanded catalogs, yet no unmistakable signature of life beyond Earth has emerged. The silence is not abrupt or dramatic. It is measured in data sets, conference proceedings, and carefully worded conclusions that stop just short of certainty. And yet the cosmos does not feel sealed or final. Each improvement in sensitivity reveals additional layers of complexity. New exoplanets enter the record, some rocky and temperate, others ocean covered or wrapped in dense atmospheres. Icy moons display subsurface oceans warmed by internal tides. Organic molecules drift through interstellar space and settle into forming planetary systems. The stage appears continually prepared, even if the principal actor remains unseen. Every discovery deepens the mystery, rather than resolving it. Identifying thousands of planets has not simplified probability, it has multiplied variables. Learning that life on Earth thrives in extreme conditions has broadened habitability, but it has also complicated predictions about where biology might arise. Improved atmospheric analysis clarifies chemical composition while revealing how many non-biological pathways can mimic life's signatures. With each advance, the question gains nuance. The quiet, therefore, becomes textured. It is not emptiness, but unresolved complexity. Perhaps life exists beneath surfaces we have yet to penetrate, or within atmospheres too subtle for current detectors. Perhaps biological emergence depends on rare combinations of events that seldom coincide. The range of plausible explanations remains broad, constrained but not closed. The question stays open because evidence has not compelled closure. In science, absence of proof does not equal proof of absence, nor does possibility substitute for demonstration. Between these boundaries lies the present condition of knowledge, provisional and evolving. Instruments still gather light. Spacecraft still cross the interplanetary dark. Data still accumulate. There is a certain clarity in acknowledging this state without embellishment. The universe remains vast, intricate, and partially understood. It has yielded stars, planets, molecules, and the physical laws that bind them. It has not yet yielded confirmation of life beyond our world. That distinction is precise and honest. And perhaps this is the most truthful conclusion available at present. The cosmos has not answered, but it continues to invite careful listening. Each observation refines perception. Each mission extends reach. The story remains unfinished, not for lack of effort, but because reality unfolds on scales of space and time that resist rapid resolution. In that steady openness, science persists, attentive to the quiet and prepared, when evidence finally arrives, to recognize it.